Once raw scores are transformed to z-scores, one of the primary purposes of a z-score is that, once you know how to interpret them, z-scores describe the exact location of the original raw score within a distribution without you having to actually know that number. The z-score transformation accomplishes this goal by transforming each x value into a signed plus or minus number so that 1. The sign tells whether the score is located above or below the mean, and 2. The z-score number tells the distance between the score and the mean in terms of the number of standard deviations. Thus, in a distribution of IQ scores with mu equals 100 and a standard deviation of 15, a score of x equals 130 would be transformed into z equals plus 2. The z value indicates that the score is located above the mean by a distance of 2 standard deviations, or 30 points. Figure 5.2 is located on page 127 in your text and shows you the bell-shaped curve, our primary reference point, with the interior mapped out using the standardized z-score values. Figure 5.2 shows a population distribution with various positions under the bell curve identified by their z-score values. Notice that all z-scores above the mean are positive and all z-scores below the mean are negative. The sign of a z-score tells you immediately whether the score is located above or below the mean. Also note that a z-score of plus 1 corresponds to a position exactly 1 standard deviation above the mean. A z-score of z equals plus 2 is always located exactly 2 standard deviations above the mean. The numerical value of the z-score tells you the number of standard deviations from the mean. Finally, you should notice that figure 5.2 does not give any specific values for the population mean or standard deviation. This is because under the z-score standardization system, all means transform to 0 and all standard deviations transform to values of 1. The z-score definition is adequate for transforming back and forth from x values to z-scores as long as the arithmetic is easy to do in your head. And you'll be working on some problems that will ask you to practice figuring out what a raw score's z-score is without using the formula. For more complicated values, it's best to have an equation to help structure the calculations. The formula for transforming scores into z-scores is shown on the slide. The numerator of the equation is the deviation score. You remember that you learned that term in Chapter 4, and I said that you would hear that term referenced again. It measures the distance in points between x and mu and indicates whether x is located above or below the mean. The deviation score is then divided by a standard deviation, population standard deviation, because we want the z-score to measure distance in terms of standard deviation units. The formula performs exactly the same arithmetic that is used with the z-score definition, and it provides a structured equation to organize the calculations when the numbers are more difficult.